Every tool in your data stack generates metadata. Your ingestion layer knows when data landed. Your transformation layer knows what happened to it. Your warehouse knows who queried it. Your BI tool knows which dashboards use it. And your governance platform, if you have one, knows what classification it carries. That's a lot of knowledge, and almost none of it talks to the rest. So when someone asks a simple question, what breaks if I rename this column? Or which of our dashboards actually use fresh, trusted data? Nobody can answer it without hours of manual investigation. Not because the information doesn't exist, it does. It's scattered across a dozen tools, stored in formats that don't compose, and locked behind interfaces that were never designed to work together. This is the metadata problem, and it's not a tooling gap, it's an architecture gap. The way most organizations store and manage metadata was designed for a world with one warehouse, a few dashboards, and a small team. That world is gone. What replaces it isn't another catalog. It's a fundamentally different architecture, the metadata lakehouse. This guide breaks down the specific problems that architecture solves, the ones you've probably already felt, even if you haven't named them yet. We've watched teams struggle with a specific version of this. They deploy a catalog, they connect their sources, and 6 months later, adoption is flat. The metadata is stale, the lineage is incomplete, governance can't keep pace, and the team that was supposed to benefit from the catalog ends up working around it. The problem was never the catalog's features, it was the architecture underneath it. That distinction is what this guide makes concrete. Before we get to the problems, we need to reframe what metadata actually is in a modern data stack, because the word metadata still carries baggage from the old world. It sounds like a side concern, descriptions on tables, tags, maybe some lineage diagrams. In reality, metadata is the connective tissue of everything a data team does. It includes structural metadata, schemas, column types, relationships between tables, operational metadata, when a pipeline last ran, whether it succeeded, how long it took, social metadata, who owns a given asset, who uses it the most, what questions have been asked about it, governance metadata, classifications, access policies, retention rules, data quality scores, and lineage metadata. The full path data travels from source through transformations to the dashboard a VP reads every Monday morning. Every one of these metadata types is generated by a different tool, and every one of those tools stores its metadata in its own format, in its own system, accessible through its own API. That is the starting condition. Not a bug in any individual tool, just the normal consequences of a data stack that grew tool by tool, each solving its own problem without coordinating its metadata with the rest. For years, the answer was the data catalog. Connect your sources, crawl the metadata, store it in a central database, put a search UI on top of it. And that worked. When the data estate was small, the team was centralized, and the pace of change was manageable, it all worked. But that model makes an architectural assumption that hasn't aged well. That metadata is something you collect periodically and store in one place, like a library indexing books. The modern data stack doesn't work like a library. It works like a living system where assets are created, transformed, queried, deprecated, and reclassified constantly, often by automated processes, not humans. The question isn't whether we need metadata management. It's whether the architecture of how we store and activate metadata can keep up. Building on that foundation of metadata generated everywhere, stored nowhere really coherently, we can walk through the specific problems that data teams hit. These aren't theoretical. They're the ones that surface in sprint retros, in incident postmortems, and in the quiet frustration of a data engineer who just spent 3 hours tracing a broken dashboard back to its root cause. Most catalogs ingest metadata on a schedule, hourly, daily, sometimes weekly. But accessing that data in reports to use it is usually a weekly or monthly pull due to the overall size. What ends up happening is the reporting on the assets becomes outdated almost immediately. A DBT model is deprecated on Thursday, the output still listed as active on Friday as the pull was from a week ago for the engineer. This sounds minor. It's not. Trust is binary. The moment a practitioner looks up a table and finds outdated information, they stop trusting. And once that trust breaks, adoption collapses. The catalog and its output becomes the tool nobody uses, not because it lacks features, but because the metadata isn't reliable enough to act on. A data engineer needs to rename a column in the core orders table in Snowflake. Before making the change, they need to know which DBT models reference this column, which Looker explorers use those models, which scheduled reports will break. DBT knows about DBT transformations. Looker knows about its own data sources. Airflow knows its DAGs, but the full path, from raw source through transformation, through the warehouse, into the BI layer, crosses 3 or 4 tool boundaries. Each tool has lineage within its scope. Almost none of them have lineage across scopes. Without cross-tool lineage stored as a unified queryable asset, impact analysis is archaeology. The engineer checks the DBT manifest manually, queries the Looker API, scans Airflow DAGs, and still isn't fully confident they've found every dependency. That process takes 2 to 4 hours for a single column change. Multiply that across a team making dozens of schema changes per sprint, and the cost becomes enormous, not just in time, but in the changes that don't get made because the blast radius is unknowable. Consider a healthcare data platform onboarding new data sources. 50 to 100 new tables appear per week. Each one potentially contains PHI or PII. The compliance team needs every table classified and access restricted within 24 hours of creation. Their current catalog runs a weekly crawl. That means new tables can exist, queryable, accessible, for up to 7 days before they're even visible to the governance process. 7 days of potential exposure, not because anyone made a mistake, but because the metadata architecture operates in batch mode while data creation operates in real time. This is the governance gap, the structural delay between when a data asset comes into existence and when governance policies actually apply to it. The gap isn't a process failure, it's an architecture failure. When metadata lives in a proprietary catalogs database, it can only be accessed through the vendor's UI and API. That sounds reasonable until a team needs to do something the vendor didn't anticipate. A data platform team at a large financial institution wants to build an internal data marketplace, a custom self-service portal where business analysts can discover data sets, request access, and understand data quality scores in a UX tailored to their workflows. They have a catalog, but its API exposes only a fraction of the metadata it stores. The query patterns the team needs, joining lineage data with freshness data with usage data, aren't supported by the vendor's API. The metadata is technically in the catalog, it just can't come out in a useful form. This is the vendor lock-in problem applied to metadata, and it mirrors exactly what happened with data itself before the open table format movement. Data locked in a proprietary warehouse couldn't be queried by external engines, couldn't be processed by custom tools, couldn't be composed in ways the warehouse vendor didn't build for. Open formats, Parquet, Iceberg, free data from that constraint. Metadata is still waiting for that same liberation. Here's a question that should be easy. How many tables containing PII do we have across our entire data estate, and which ones haven't been queried in 90 days? That question requires 3 types of metadata: governance metadata, PII classification, operational metadata, last query date, and structural metadata, table inventory. If those 3 metadata types live in different systems, the governance platform, the warehouse query history, and the catalog, the question can't be answered with a query. It requires a manual investigation across 3 tools, probably involving spreadsheets. Now, scale that. An organization with 10,000 tables, hundreds of dashboards, and dozens of pipelines. At scale, the basic question a data team needs to answer about its own data state, what's trusted, what's stale, what's the blast radius of a chain, what's compliant, can't be answered. Not because the knowledge doesn't exist, but because metadata isn't stored in a format that supports composition and programmatic access. Now that we've named these 5 problems, staleness, lineage fragmentation, governance gaps, vendor lock-in, and the inability to compose metadata, we can look at the architecture designed to solve them. And the clearest way to understand it is through a parallel most data practitioners already know. The data lakehouse emerged because organizations outgrew both the data warehouse and the data lake. Warehouses were structured and reliable, but expensive and rigid, with data locked in proprietary formats. Lakes were cheap and flexible, but unreliable. No ACID transactions, no schema enforcement, no time travel. The Lakehouse combined both open file formats with warehouse grade reliability, separation of storage from compute, and support for multiple query engines on the same data. The metadata lakehouse applies the same principles to metadata itself. Instead of storing metadata in a proprietary catalog database, it stores metadata in open table formats. Think Apache Hoodoo or Apache Iceberg applied to the metadata layer. That single architectural choice unlocks several capabilities at once. First, metadata gets full transactional integrity, versioning, rollback, and time travel. We can ask, what did lineage look like last Tuesday? Not as a theoretical exercise, but as an actual query against the metadata store. Second, storage separates from compute. Metadata enrichment, classification, lineage computation, policy evaluation runs as independent compute layers on top of the stored metadata. Each of those operations can scale on its own, instead of being bottlenecked through a single system. Third, open formats means metadata can be queried by external tools, not just through the catalog's UI, through SQL engines. The metadata becomes composable infrastructure, not a locked asset. And fourth, this is where the governance gap closes. The architecture supports active metadata, allowing for automation. When a new table appears in Snowflake, that event propagates to the metadata lakehouse in near real time. With simple scripting, identifying those updates can trigger events, such as automatically tagging assets for your new columns that contain confidential data. This is what Atlan has built its platform around. Not just a catalog with more features, an architectural shift in how metadata is stored, versioned, queried, and activated. Building on that architecture, we can look at what it actually enables. Capabilities that weren't just difficult before, but structurally impossible given the old approach. Impact analysis in seconds, not hours. That data engineer renaming a column in the orders table, with cross-tool lineage stored as a first-class entity in the metadata lakehouse, not derived on the fly, but persisted in queryable, the blast radius is a single query. Every downstream DBT model, every looker explore, every scheduled report that depends on that column returned in seconds with full path visibility. Real-time governance that matches the pace of data creation. New tables are detected, classified, and policy controlled within minutes of creation, not days. For that healthcare platform adding 100 tables a week, the governance gap shrinks from 7 days to near zero. Compliance stops being a retroactive audit and starts being an automated, continuous process. Composable metadata queries. That how many PII tables have not been queried in the last 90 days question becomes a straightforward query against the metadata lakehouse. Join classification data with usage data with ownership data. Filter aggregate, export. Build a dashboard on top of it. Schedule it. The metadata is queryable the same way data is queryable because it's stored the same way. Custom applications on top of the metadata layer. That data platform team building an internal marketplace doesn't need to work around their catalog's API constraints. They query the metadata lakehouse directly, build the exact UX their analysts need, and extend it as requirements evolve. The metadata layer becomes a platform, not a product boundary. And the capability that's accelerating fastest, AI that can reason over complete context. Large language models applied to data for natural language queries, for automated documentation, for intelligence governance suggestions need access to a complete connected metadata graph, not fragments scattered across tools, not stale snapshots from the last output and crawl, a live, unified, queryable representation of every asset, its lineage, its governance state, its usage patterns, and its relationships. The metadata lakehouse is the foundation that makes this feasible. Without it, AI in the data stack is guessing with partial information. What ties all of this together is a simple shift in how we think about metadata. It is not a byproduct of the data stack. It's not a feature of a catalog, it's infrastructure with the same architectural requirements we've already learned to apply to the data itself: open formats, separated storage and compute, event driven processing, and multi engine access. The metadata lakehouse is what happens when we finally treat metadata that way. The 5 problems we walked through — staleness, broken lineage governance gaps, vendor lock in, and the inability to compose metadata — aren't separate issues. They're 5 symptoms of the same architectural gap, and the metadata lakehouse is the architecture that closes it. The next question is how to evaluate whether your team actually needs it, and how to adopt it without a full stack rebuild. We've got a guide on that coming. And if any of this resonated, drop it in the comments. What's the problem that's costing your team the most time?